Okay. This is a picture I showed earlier when I first started talking about the shelf edge deltas. And here's the general model that during a low stand of sea level, you'll have subaerial exposure of most of the shoreline. So you have these valleys carved out that supply sediment across the exposed shelf, and that sediment gets kind of dumped out right at the shelf edge, or the shelf margin. So I've drawn three of them here, colored in three of them. And what I want to show you now, relate this a little more to reservoir quality. We would call this end of a delta, shelf edge delta, the proximal end. And again, I'm not a very good writer here, so it's Proximal. And then the distal end, the down dip end, or the distal end, is being down here. And what I want to show you is variations in reservoir properties that you get as you go from proximal to distal environments on that shelf margin delta. So here we are. This particular one I'm going to show you occurs in the northern Gulf of Mexico, a shelf edge delta. And you can't probably see this very well, but if you've got the computer there, you can. What you're looking at here is distal delta. Let's see if I have. I'll just put a D for distal delta and a P for proximal delta. The proximal delta is going to be closer to the source of sand, so as you might expect, you're going to get more sand in the proximal setting. And as you go from proximal to distal, your amount of sand is going to decrease. So if your reservoir target was a shelf margin delta, you would want to probably, based on that, you would want to probably drill in the proximal end, because the grain size, you're going to get more sand, probably be coarser grained also, and less sand down here. Well, remember that sand affects your permeability. The coarser sand that'll be deposited in the proximal setting then would be expected to have a higher permeability than the sand, the lower amount of sand that's in the distal levee. So let's look at that. So here's the proximal levee. This is a core description. And what you see is, like I said before, is an upward increase in grain size and bed thickness. Again, I sure wish I could draw a straight line. I missed that day in school, I guess, when they taught us how to do that. So at any rate, you are getting cleaner upward, more sand. And that sand is going to be relatively coarse grained. And so if you can't see this on the board, I'm sure, but this heavy black line is permeability, going from low at the right to high to the left. So very high permeability on the order of 100 millidarcies or so. And then that permeability drops off as the amount of sand drops off, or is lower. So again, an indicator that your best reservoir in one of these deltas is the upper part. By contrast, Here's a picture of distal levee where you've got much less sand. See, there's only a little bit of sand here, much less sand. It's going to have finer grain size, and therefore the permeability is going to be less. And so the black line here kind of runs like this. And the permeability is on the order of 1 millidarcy. So there's been 200 or two orders of magnitude change in your permeability from the bottom to the top of the reservoir. And so that's a lot. Also, your net sand is increased. And so once again indicating that in the proximal setting, especially near the top of the delta deposit, you're going to have your best reservoir quality. And as you go further down dip, your reservoir quality and your sand amount is going to decrease. Well, we can express that another way. Let's express that this way, where the green dots here are proximal delta front, and they all occur up here. And the red squares here are distal delta front, and they occur down here on this porosity versus permeability cross plot. So you see again, you even have some values that are almost 1,000 millidarcies in the proximal delta, and they go down to about 2 millidarcies, but on average, most of them are around in the 100, 150 millidarcy permeability. Whereas down here in the distal, here's 1 millidarcy down there, and 0.01 millidarcy down there, and so most of your data kind of falls in this range. So, and that's an important, and once again, I point out that the sand content, as you go up from distal to proximal, the sand content goes up. So those are all important reservoir properties. Okay, so if you determine that your reservoir is one of these shelf margin deltas, and you say, well, where should I drill? You don't want to drill it in the distal setting of the delta. You want to drill it in the proximal setting. And if you have seismic, you can usually determine which is proximal and which is distal. And the same way, just with well logs, these are not well logs, but you can imagine that you'd have a log with a very nice cleaning upward pattern for your proximal delta, and more of a shaly pattern with a few little spikes for your distal delta. So you get that distinct difference in well logs also. Well, what's the implications of this? In this particular case, you get porosity as high as 27%, permeability as high as 766 millidarcies, and this just tells where the sands are in terms of depth. And that's about the implications, that you've got really good reservoir. Now, one of the things that I object to, I'm going to give you another little tip that things that I don't like, is when somebody comes to you and says, this is the porosity of my reservoir. 27%, we'll say. Okay? I hope by now you got the idea that that's not the case, and that it's a meaningless number when you say average. Now, I've seen this a lot in, I don't know how your company works with buying or selling properties for production, But I've seen a lot of cases in the U.S. where, say, a company is looking for money to drill a well. So they go to the banker there and shows the banker, here's my reservoir, it's got 27% porosity. And the banker pulls out in his side drawer, he pulls out a piece of paper and says, I just got another bid from someone who's got 30% porosity. Okay? So I'm going to buy theirs and not yours, you know? And so that means nothing. It's the porosity profile that's important. Where that high porosity is, where the low is, means absolutely nothing when you give porosity a single number, or even if you put a plus or minus with it. That still doesn't tell you where the distribution of that is. The high porosity zone may be very thin, or it may be very thick. But that's the information you want to know. You don't care about these averages. And it's even more important with permeability, because permeability is so sensitive, like I said the other day, permeability is so sensitive to changes in grain size that a small change in grain size can change your permeability by an order of magnitude or so, or more. And so that's one of the implications here, is you don't really want to use averages. At least in my opinion, you don't. And I've seen an awful lot of cases where some properties put up for sale or for lease or what have you, and they'll say, oh, I got a fantastic reservoir, 27% porosity and 766 millidarcies permeability. And if I have the chance, I'll say, show me the profile. And sometimes it might be based on one data point, taken randomly in the sand. And sometimes it can be a very good profile. And so you can see the distribution of your reservoir quality. So be wary of these averages, because at least in my opinion, they don't mean very much. And when you do an average like that, the tendency is for you to, and you're building a model, a reservoir model, the tendency will be for you to put that number, upscale your sand body to that one number, rather than go and see what the distribution is and then break out different zones of porosity and permeability, which is what you should do when building a model, a reservoir model. Okay, let's see. Let's see where I am here. All right, well, this is one of my very favorite diagrams. Love this diagram because in this one picture, it shows about everything I've been talking about so far in kind of a conceptual manner, but a realistic manner. And it's also going to become very important when I start talking about sequence stratigraphy. So you'll see this diagram several times. What it shows you, what it's meant to show you, is the distribution of sand and shale through one complete sea level cycle, where you go from the top of a sequence down to the bottom of a sequence. And this would be a sequence that you would have in non-marine and very shallow marine deposits, just like you guys work with. When you get out into deep marine, things are a little bit different. But in shallow marine, this is a very good conceptual model to use. Obviously, there's more detail, but this is a very good conceptual model to tell you where the sands are going to be and where the shales are going to be throughout a depositional sequence. So we start out, let's just start out with a falling stage of sea level. I don't have much room to draw a sea level curve here. maybe I can. I'll put in a sea level curve here. I talked about those this morning, where we have rising sea level. Where we have rising sea level, rising sea level, that doesn't work very well. One second, let me do my drafting skills here. Okay. High stand of sea level is going to be up high here on this curve. Low stand of sea level is going to be down here. So your vertical axis goes from a low stand of sea level to a high stand of sea level. And with that sea level cycle, you deposit one depositional sequence, all or part of a depositional sequence. So let's start now by we'll start dropping sea level. Well, what's going to happen when you drop sea level? Remember way back this morning, or maybe even yesterday, you get that erosion surface carved. You drop sea level, the shoreline moves seaward, and you create a valley, and that valley will have erosional topography on it. So you develop this incised valley. And that's going to occur in this falling stage of sea level, down here. Now, let's turn around and start to raise sea level. And what's going to happen first? Well, you're going to backfill your incised valley. And remember, in an incised valley, as you backfill, the environment within that valley becomes lower and lower energy. So you end up with your coarsest beds on the bottom. Remember, fluvial deposits. And then as sea level rises, you get some encroachment of the marine environment, so you get finer grained marine sands. And what's that going to do? That's going to change your permeability. So you're going to get lower permeability as you go up through that valley fill. What I'm doing here is I'm summarizing everything that's talked about today. Then, if sea level continues to rise after you fill this valley, sea level is continuing to rise, and so back here you develop, in the non-marine environment, you develop a floodplain. In the marine environment, you have marine water, and as sea level rises, remember your transgressive sands are kind of stepping in a landward direction. These will be those nice transgressive sands like we found in the PMEX example that I gave you. And they're in the shoreline, and they step in a landward direction with time. Now back here, behind those sand bodies, it's not just empty space, but you've got sediments and environments. So back behind those shoreline sands, you're going to get floodplain deposit, maybe with some meandering river deposits now, because you're in lower energy. Your still sea level is rising, So your energy levels are decreasing, so you go from braided river to a meandering river system. More lenticular sand bodies of lower permeability than what you had down in the incised valley. These will be very good sands because they're reworked by the transgressing sea. Well, and that's going to occur down around in this part of the curve. Well, at some point, your sea level may continue to go up, but the rate of change of sea level starts to drop off. And so the slope of my curve, if I had drawn this properly, the slope of my curve would be less as we come up towards the peak here. But at any rate, at some point around in here, where you have a steep slope of your curve, that's going to be where you get the maximum landward extent of that shoreline due to transgression. The shoreline will not go any further than that, more landward. Again, here's land, and there's sea. Well, what kind, in a non-marine setting, what kind of environment are you going to have where you have a maximum landward extent of the shoreline? It's going to be a very low energy environment, probably going to be coals and swamps and lakes. Okay, so the lowest energy environment. So the black area here represents lakes or marshes or swamps, things like that. Then at that point, when your rate of change of rise of sea level starts to diminish, you start to prograde. In other words, at this time now, your sediment supply, you've got a certain amount of sea surface to sea floor, and your sediment supply is going to build out and cause progradation. And when you prograde, what's going to happen at the shoreline, you're going to get these deltas that prograde seaward. Or if there's no major river around, you're just going to get things like beach sands or something, but they're going to prograde in the seaward direction. And following behind those will be some more of the floodplain with some more of these meandering sands. So that's a profile. We could take this profile. We could put the different permeabilities, relative permeability. I hate to use the term relative permeability to engineers because I'm talking about something else. Talking about 10 millidarcies relative to 100 millidarcies, something like that. So I could change this chart into a graph of permeability. I could change it into a graph of porosity. I could change it into a graph of showing the expected lateral continuity, again the relative lateral continuity, and where you're going to get your seals, where you're going to get your hydrocarbon source rock, and I can do all of that with this cartoon. Well, it turns out the cartoon is pretty accurate, and there's an awful lot of depositional systems that conform to this general pattern. Now, it's just a model, a conceptual model, and but it's based on a lot of studies, but you can get variations, slight variations about that general model, and the model will still hold. So for this reason, that's one of the reasons I like this as a screensaver. To always remind me to think in terms of sequence stratigraphy when I'm doing reservoir studies. And it's a very simple diagram. You should all have this all figured out by now. There's nothing on here that I haven't talked about, and this is one diagram that summarizes it. Well, excuse me, there's one thing I haven't talked about, and that's what these are, SB, HST, and all that, and that is the sequence stratigraphy part. So in essence, you've got, if we go to the marine environment here, what have you got? You've got a wedge, where with transgression, your shoreline's moving landward, so you're depositing shales seaward of the sands, seaward of the shoreline sands, and then here you're depositing shales seaward of the shoreline sands. So you end up with like a wedge like this, sedimentary wedge. So in this case, if I drilled a well, say I drilled a well now, and I'm going to drill my well okay, I'm going to drill a well right here. So I drill a well right there. What is my well log going to look like? Well, you're going to get some nice, good, clean sands. Start to back off into shale. You might get a little sand kick, and then back into shale, and then a nice sand, back into shale, and sand above. So that's what your well log is going to look like in a setting like this. Once again, I stress that even though you've got sands here, they do not have the same properties. The properties of this lower sand is going to be different, for example, than the properties of the upper sand. Very, very important point that is often overlooked, particularly when building reservoir models where you upscale and you tend to say, well, each sand body is the same, so I'll just put the same values in for my model. Not true. Suppose I drill a well, now let's drill a well right here. And I'll get a little bit of sand, good sand, and some shale. Get a little more sand here, and more sand up there. Oops, no, I didn't do that right. Excuse me, it'll be like that. So that's the way a log would look like right there. And if you understand this, it makes your correlations much more realistic. Now, when we get into sequence stratigraphy next, what I'm going to give you one definition here. Okay, well, where in this depositional sequence, where is the maximum landward extent of the marine shoreline? It would be right here, where the lake meets the ocean, okay? That's defined as the maximum landward extent of the shoreline. It has a name. It's called it's the surface. That surface is called a maximum flooding surface, MFS. And it's a term that I'll use quite a bit now for the rest of the course as we get into more detail. So maximum flooding surface, meaning the maximum landward extent of the shoreline, okay? Maximum, and it's a surface, it's not a rock, it's not a bed, it's a surface on top of a bed. Okay, so these maximum flooding, yes sir?
Sometimes we use the MFS like this.
As what?
Like a sequence, like a different sequence.
Ooh. Uh-oh. You must have read papers by the guy at Texas. I'm going to talk about that later on. No. Well, before I say that, okay. Bill Galloway. Somebody must have read Bill Galloway if you call that a sequence boundary, an SP sequence boundary. I think I know what you're getting at, but I'm going to not explain it that way right now. But let me explain one thing. The two leaders in sequence stratigraphy were, number one, the exxon geologists, and they're the ones, the story goes something like this. I have to tell you the story. That there was a guy, a professor, geology professor, very famous by the name of Larry Slatt, and he taught stratigraphy. And he understood sequence stratigraphy way long before anybody else. Well, he had got a group of PhD students that included people like the great Peter Vail. Maybe some of you have heard that name, Peter Vail, Mitchell, Sangri, a whole bunch, about 6 or 7, Posmentier, a whole bunch of really top flight people. And they were all PhD students of this guy Slatt. And he taught them the significance of time, of geological time in correlating. And when they all graduated, Exxon went and hired them all. And the Exxon senior manager, now this was back in about 1976 now, so we're going back. But at that time, the Exxon manager said, tell me about this stuff, this seismic. We've been using seismic for many years for structural interpretation. But I wonder if those reflectors have any stratigraphic significance. Prior to that time, people were picking faults and folds and things with the seismic, but not really looking at if there was any stratigraphic features that could be picked out. Well, so what they did is they took all these guys, they took Peter Vail and Sangri and Mitchum, and they locked them away somewhere in a private building, and the management said, come on out when you have an answer, either yes or no. There is stratigraphic significance or there isn't. And then we'll feed you that time. So they spent about 2 years starving. And they came out with a book in 1978, or excuse me, the book was out earlier, but it wasn't published till 1978, called Seismic Stratigraphy. And what they had determined, they looked at wells and outcrops and so on all over the world. And what they found out was that there were, you could go to one place in the world and determine, generally by the fossils were very important, just like we use them today. They could determine that when in one part of the world you had a drop in, or a change in sea level, either a drop or a rise, you could go to another continent, and at that same time, you would have another rise and fall of sea level. So it became known as kind of a global, this sequence stratigraphy, these fall and rises of sea level were global in nature. They occurred all over the world. Now, you've got a little bit of a kicker in there because tectonics, local tectonics, can change your sea level if you've got uplift or down or subsidence or what have you. But on a global scale, they recognized, and I'll show you a map of this tomorrow, I guess, probably. They went to enough different parts in the world to determine that the changes in sea level were of a global nature. And there were reasons for that I'm not going to get into here. There are plate movements on the seafloor, climate changes, all kinds of reasons for that. Well, so the Exxon people then became very famous, very popular, and they applied some names. I'm getting around to your question here now. They applied some names to these rock sequences. And one of the key ones was this SB, or what's called a sequence boundary. An erosion, I've been calling it an erosion surface, but sequence stratigraphers would call it a sequence boundary, just like you called it a boundary. So here you have a sequence boundary at the base of a sequence, and a sequence boundary at the top of the sequence, and everything in between is one depositional sequence where you had a fall-rise cycle of sea level. Well, everybody was happy with that, except for these Texans. You know, they got to be different. And so there was this guy, Bill Galloway, who was a famous, excellent sequence stratigrapher, very famous. But he had one flaw, in my opinion, and many other people's opinion, he had one flaw. And he said, I'm going to be a little bit different. What I'm going to do is say that what Slatt just called a maximum flooding surface, which is really the Exxon folks called it, I'm going to call that a sequence boundary. Oh man, did that ever throw the geologic world into a tizzy? Because then you had to ask, just like I asked you, whose sequence boundary are you talking about? Galloway's sequence boundary or the Exxon sequence boundary? Did it matter? Sure it mattered. Made a big difference. Because what you're ultimately trying to do when you're developing a sequence framework is predict. You want to predict what the geology below a boundary is and what the geology above a boundary is. You find these significant boundaries and then predict what's above and what's below. Well, so if you have a Galloway sequence boundary, you're going to have a progradational unit above and a transgressive unit below. Well, if you've used the Exxon, you're going to have a falling sea level here. You might have a rising sea level down there. Just the opposite. So you really have to know which sequence boundary. And for many years there were all kinds of debates and arguments about that. Whose sequence boundary are you talking about? And I give a lot of the courses people who had either graduates of Texas who had taken Galloway's sequence stratigraphy course, or people who had taken a short course like I'm given here, and always would get confused. You know, whose sequence boundary are you talking about? So that's partially the answer. There's another part to it that I'm not even going to get into now. I'll talk about it when I talk about unconventional resource shales. But there is another aspect of this. But this is the main aspect, and that's why I jumped on it as soon as you said that. Oh my God, we got to start talking. Must be a Texas graduate or something.
French guy.
Huh?
French one.
Professor, or maybe a too easy question, but what defines then a sequence boundary?
How do you define, or how do you recognize it?
What does define a sequence boundary? When does it start running? Yes.
Well, when is it going to start? See, now I call it, it's a sequence boundary here. I mean, you can answer that question. Let's see, now what I want to do. Okay, it's called a sequence boundary here. What was I calling it earlier? I've been calling it an erosion surface or an unconformity, meaning erosion. So a sequence boundary by the Exxon definition is an erosion surface. And you can usually see these in cores and in well logs and so on. You get sharp breaks in your well log and things like that. And this was an important point. I'm glad you mentioned that because now I can do more of this. Galloway had Galloway was not just a nasty guy, you know, that wanted to be a contrarian. He had a reason for doing this. And he said, well, it's easy for me to look at a well log, and usually that maximum flooding surface is going to be the top of a big shale. Okay? So I'm going to do correlations, and because, well, the maximum flooding surfaces tend to be very aerially extensive. And so if I've got a couple of different wells, I'm going to use that to correlate. It represents more or less somewhat of an instant in geological time, so it's a great correlation marker. So that's why I call it a sequence boundary. That's what Galloway said. The Exxon folks then got up at a conference and said, well, great, but you can't really see this feature on seismic unless it's really, really thick. If it's really thick, you'll get an amplitude. But unless it's really thick, you don't see any seismic reflector. And the Exxon guy said, but we can see a sequence boundary really well. It's an unconformity surface. So you might have some beds below that are dipping this way, and then some beds here. There's your sequence boundary. And that was the answer. Somebody got up and said, the Exxon folks use seismic along with well control. Galloway did everything with logs. He hardly used any seismic. And so it was a matter of using different data sets to try to do the same sort of interpretation. And that's what caused the controversy. And I think the Galloway approach is not usually used anymore, as far as I know. More people stick with kind of the Exxon approach to sequence stratigraphy. So that answers your question, I hope. It's an unconformity surface. So if I were to have a well log, say a well log through here, down to here, and I hit that sequence boundary, usually it's going to be a very sharp surface. So you might have a shale down here and then a very sharp base sand, something like that. But in the areas where Galloway worked, these maximum flooding surfaces were quite abundant, quite easy to see on the logs. And so his mistake was calling it a sequence boundary. If he had called it an apple or an orange, it would have been okay. But he said, no, I'm going to use the word sequence boundary, and it caused all this confusion and everything. So I don't know if that helps answer the question. There's still another part to it that I'll hold off on for now. But that's basically the issue. So if you call a maximum flooding surface a sequence boundary, then you're a Gallowayian person, okay, and an Exonian if you call the sequence boundary down there. So I'm an Exonian myself. So this green line then is your maximum flooding surface. And remember the definition, it represents the maximum, it's a surface that represents the maximum landward extent of the shoreline, which in this picture would be right there. You've got a lake environment landward of that, and a marine environment seaward of that, at that particular horizon. What's neat about it that we'll look at is that because these maximum flooding surfaces are normally surfaces of shale. Why is that? Because you're getting a lower energy environment as you get closer and closer to this maximum flooding surface, your stratigraphy. Well, where do fossils like to collect? Well, they collect in shale. They don't collect in sand. You don't often find as many in sand because sand being porous and permeable, a shell like one of those oyster shells may be deposited, but with burial, there's a good chance it can be dissolved away. So you don't see it in sand. So if you're looking for fossils to age date or to correlate, you look in the shales. And the best shale of all to look in is this maximum, is the surface on this maximum flooding surface. Now I may as well introduce one more term which you're probably familiar with. So if here's our maximum flooding surface, it's a surface of a shale, take my word for it. And this will be the shale. So there's the top of the shale and the bottom of the shale. Well, that interval is usually going, because it represents the deepest water depth in this sort of an environment, it's going to contain a lot of organic matter along with the shale particles. Organic matter is very lightweight, organic particles, so they tend to settle in the lowest energy environment. So what you do is you identify a maximum flooding surface, and then you look in the shale below for the fossils. And that shale is a specific shale that has a specific name. I'll call it a CS. This condensed section is what it means. CS for a condensed section. It's defined as an organic rich shale that represents kind of the maximum landward extent of the shoreline, which is capped by the maximum flooding surface. Okay, so this is the maximum flooding surface, which is also the top of the condensed section, and this is the bottom of the condensed section down here. Very important. First of all, maximum flooding surfaces are aerially extensive. They're usually marine, so they're going to have fossils in them, and they are the top surface of an organic rich condensed section. So they all often make good hydrocarbon source rocks, because you got all that organic matter, and they also make good correlation markers because they're laterally extensive and they're organic rich shale, so you get a very high gamma ray peak usually. And that's what you want to do your correlations on. So if you're correlating, if you're doing stratigraphy and seismic, you want to look for those discontinuities of the reflectors. If you're looking on well logs, you look for these high gamma peaks and you correlate on those. Yeah.
So if we were to work on looking for unconventional reservoirs, these are parameters we gotta keep in mind.
These are the unconventional reservoirs. They're all condensed sections. Okay, they're condensed sections. Now they can be 1,000 feet thick. Still represents a rising sea level. Okay, up to this maximum landward extent of the shoreline. So this is exactly where all of your unconventional resource shales occur.
Taking into account what you mentioned that the fossil or the organic material, because of the size, may drop. Is it safe to say that we may find most of the organic rich shale at the bottom of that specific column?
Top.
At the top.
Yeah.
Okay.
well, I'm going to modify that now a little bit. In terms of a big thick sequence, usually near the top. But when you start breaking down, and we actually see this a lot, and I'll show you some of this on Friday, actually when you break down to smaller and smaller scales, the most organic rich part is on the bottom. So generally on the top, specifically down towards the bottom. But if you understand sequence stratigraphy, you can use sequence stratigraphy for shales, okay? You can do it. And if you understand that, you can predict where your source rock is going to be, where a seal might be, where you don't have organic matter, and so on, within the shale. Up till about 10 years ago, people used to think shales were homogeneous, just uniform black shale. But now we know that's not true. They're very highly stratified, and they're very complex. That's one of the areas that we've been studying now for several years, and other people as well. So, but in the general sense, the condensed sections are your resource shales. So right there, that tells you if you've got a seismic line, and you can develop a sequence, find the sequence boundaries, okay, find two sequence boundaries in the seismic line, somewhere in there is going to be your potential unconventional resource shale between those two boundaries, okay, just because of the way the rocks were deposited. If you use the Galloway approach, if you've just got well logs where you get the big high gamma ray kick, that big gamma ray kick will be your condensed section and resource shale. We'll take a little break because there's some food there to get your nourishment up, and then we'll go just a while till 5:30 again.